Is this on now? Yes. So here I would like to point out a particular issue which is not being studied so much, and partly it's because we don't have a good idea about it. So here I would like to first of all indicate what the issue is, what's bothering some people, and potentially some ideas maybe that can be helpful in getting there. So to do that, I have to phrase what the issue is, and to do that I have to give you a background of what motivates the question. So as you well know, dualities have played a key role in our understanding of string theory in the past couple of decades, and so we have increasing understanding of what dualities mean and how they work. And by now there's no doubt they're correct, even though almost none of them we can prove. So anyhow, we understand something, and but the basic. So I want to first of all review the basic gist of common feature of all dualities. So you start with two sides at least. So the side A, let's say side B, and the two are supposed to be identical. Side A and side B are the same theory. It's just that the regime in which side A is simple, so maybe when the coupling constant is small, and the side that B is useful is when the other one, this coupling on the B side, is small, and typically they are related by some change of parameters. Like the most simple one is like G prime is 1 over G, and so when this is weak, this is strong, and vice versa. So easy description of a physical system on one side necessarily means strong or hard description from the other side, and vice versa. So in this way, dualities have become very useful in trying to solve a problem. If you want to study problem B when G prime is large, you just study problem A at weak coupling, and that's the solution. So dualities have turned out to be solutions to hard problems. That's why we're interested in dualities, to solve it. Not just because there's a duality. If they're both equally hard, then we wouldn't gain much. So this is a general picture. Now, one feature of these is that there is no point in which two descriptions are both weak. In other words, if you have two simple descriptions at the same point, it becomes strange. So in other words, there's roughly only one good description at a given point, at most. In other words, if G is small, you use this. If G prime is small, you use this. There's no point in which both are simple. So they're like mutually exclusive. There's only one good viewpoint at a given parameter space, at most. Sometimes there's no good viewpoint. For example, if G and G prime are both equal to 1, at that point, both are hard to describe, and we don't have a good description at all. So it's not like at every parameter space there's one simple description. Sometimes there's none. But if you have two different descriptions of the same system at the same point, they're weakly coupled, that'd be strange. So we don't have that. So usually there's this map between them. So there's only one good description at a point. So this is a general feature of dualities, yes?
Why can't we have two parameters, for example?
Yeah, we can have more parameters. But the main point is that where one description is useful in terms of having a weakly coupled description for all quantities, the other one is typically not so. In fact, never so. So in other words, it would be strange to have some simple description of in two different languages, the same language. You could still have more parameters, but typically you don't have the same theory at some point being weak in the same sense. So there could be more parameters, but you have to define what weak in each parameter regime means. So you have to define. I'm just trying to describe it in terms of one parameter, but you can generalize it. Still, there would be something called weak parameters, weak couplings. So this is a general feature. And then there's moreover democracy of dualities. Neither side is better than the other side. It doesn't make sense to say, no, the theory is really B. Just A just happens. No. It's just they are the same, okay? You just don't say which one is better. You're just all equivalent. We don't take that view. So I would call that democracy of dualities. Democracy of dualities or democracy of theories. So none of them is really better than any other one. Now, of course, for certain questions, one side is definitely better than the other one. I'm not saying for every question everyone is equal. That's not what I mean. But as a whole package, you don't say this is the right description. If you focus on a given question, yes, then there will be perhaps a right one, but not as a general statement. Okay, so that's just a general statement about what dualities have been. And one thing I should say is that to try to describe A when G is small, it's going to be very difficult to use B. It doesn't mean you cannot try to. So if you try to use B, you have to try very complicated constructions to try to give a description of it. So I will give you just to give you an idea about what I mean by that, I'll just give you a simple example. This is basically T-duality where we understand it. It's one of the very few dualities we can actually prove. So T-duality, as you know, is that if you compactify a theory on a circle of radius r in the string context, this is related to a same theory where the circle is changed to 1 over itself. This is in some theories. Sometimes it's exchanged type 2A with type 2B, or heterotic is the same. Anyhow, I don't want to get to the basic details, but there's this duality, r goes to 1 over r. Okay, so what is about this? Well, you have a space of some radius r. If r is much, much bigger than the string scale, then the good description is in terms of that space. You use the space in which the space is big. Of course, it's equivalent to the space is small. So if you have r prime is 1 over r, which is a very tiny circle, they are equivalent. Now, there's one useful description, namely this one, when r is big. So why do I say that? Well, the light modes are objects which are like waves moving on this. For example, if you have a light package sent around the circle, you use a localized light beam. Of course, this is equivalent to the same thing here in the R prime language. What do you do there? A wave packet that you send around is made of momentum modes. But in the dual description, this is made of winding modes. So indeed, you can say, oh, you know what? I will take winding modes, and I take some superposition of the winding modes to define a position in the original space. So you take an infinite combination of these winding sectors of the strings, and then you say, oh, this is just a point here. And then this wave packet grows. You cannot even visualize it from this side. So it's equivalent, but silly to describe it this way. Is that clear? So we describe it in terms of the usual wave packet in the physical space. But it's equivalent. There's no problem. The duality is there. This is one of the few cases we can actually write down the analog of this state, the analog of this position state, in the original theory in terms of the winding of the other guy. Is that clear? Okay, so this is a lesson here. So it would be possible but not useful to try to write it this way. That's my point here. So I want you to take that lesson from here. Okay, now I want to give some historical perspective to how string theory evolved. So this was, I will take you back to early days of string, namely pre-duality era. Not very early, but mid 80s, let's say. So in that case, what did we have of string theory? Well, we had a bunch of string theories, and they seem to have, all of them seem to have graviton as excitation, and but in general they had much more than graviton. So you had some m squared equal to 0 state and some other states which are higher and higher excitations of strings. There are many different states. And why did we believe string theory is a good theory of quantum gravity? Was 1, there was a graviton. 2, there was a coupling constant G, in string coupling constant, for which we could expand to arbitrary high perturbation order any quantity we wanted to compute, and the computations all made sense. There were no divergences or ultraviolet divergences. Things make perfect sense. So we got a perturbative scheme to compute everything to all orders in G. This was an amazing statement. It just meant we have understood at quantum gravity at least perturbativity to all orders in perturbation theory. That's why people like me and many other people were studying string theory, because it's a good quantum theory of gravity. This is a strong evidence for it. Now, this was not satisfactory back then completely. We believed they exist because we had a perturbation series, but we want to have a non-perturbative definition of the theory. So people tried to write down string field theory, whose perturbation gives you these diagrams, which allow you to define what you mean by non-perturbative strings, just like what we usually do in quantum field theories. So people wrote down string field theories and generated them, but none of them were natural. So even though in principle one could write down the analog of string field theory, it didn't look a very natural construction. So there was some progress, but there was always this worry that doesn't look very, it wasn't, no new principle emerged from that. So it sounded like a little ad hoc. Except for open string field theory, which turns out to be somehow related to Chern-Simons theory abstractly. Within Chern-Simons, string field theory was a very interesting conceptual description of field theory. But for closed string sector, namely graviton, we didn't have any such nice description, even though there were some progress in that direction as well. But anyhow, this was the status of things when duality hit us. So the fact that, so the leading order description of string theory involved a degree of freedom having to do with the Einstein, where G can be viewed as related to dilaton, and there's Einstein term, and so there's other fields and other terms you can write down. So the fact that we had the analog of this Einstein's action as the effective theory was a feature of the three diagram amplitudes, which are spheres, whatever you want to compute, gives you the effective theory of gravity, which we believe. But as I said, it's much more than that. We could do perturbation series. So we don't view string theory as an effective theory. We view it as a complete theory. It's just that we just only know how to compute perturbatively. Is that clear? So it's not just an effective theory. So just like description of the weak interaction in terms of Fermi model for them, the quartic fermion terms, that would not have such a feature. You would not get a consistent perturbative description. That I would have called is an effective description of weak interaction. But here, we are getting a complete description in the sense that at least to all orders in perturbation, we know how to deal with it. Okay, then I want to step a little bit back, actually, in mid-70s. So this is when 't Hooft was studying large N gauge dynamics for SU N gauge theories. And he noticed that if you take the N to be much, much bigger than 1 and the coupling constant of Yang-Mills to be much, much less than 1 in such a way that their product is held fixed, you fix lambda and you take these limits. Then what happened was that the perturbative expansion of gauge theories organized themselves in terms of Riemann surfaces. As you know, for example, you'll get these 't Hooft diagrams, which are these gauge bosons, which are viewed as a double line because there are two indices, and you can basically view them as when you write the diagram as a Riemann surface with holes, where these holes are left by the boundaries of these diagrams. So 't Hooft's insight was that, this looks like string theory. So they had already discovered string theory, and at that time it was called the dual models. So in his paper he says, it could be that this is somehow dual. He doesn't use the word dual. He said, it could be that this is related to the dual models, dual resonance model. Okay, he didn't call it string theory. Okay, why? Because it looked like string theory. Okay. And his idea was that somehow the strong interaction will force these quark-anti-quark pairs, the boundaries of these open strings, to close the gap, smooth out the surface, and you get a closed surface. That was the picture. So he said, in fact, it's possible that these dual models are somehow a solution to the gauge theory problem. So the question for him is, can you use those models as a solution? So the question was, can string theory be a solution to strong coupling, to gauge theory, strong coupling problem, and in particular in the regime where the coupling is much, much bigger than 1, lambda is much, much gets bigger. Okay. Now, we learned through beautiful ADS-CFT duality that the answer for that is indeed yes. So this Maldaceno's in particular shows that if you take n equals to 4 Yang mills, the theory of in 4 dimension is dual to ADS5 times S5 type 2B theory on this ADS5 times S5 with suitable parameters and fluxes and so forth. So this was a beautiful, concrete realization of the dream that a 't Hooft has in terms of how you actually solve a gauge theory problem. Namely, the strong coupling regime of this gauge theory is given by a string theory. String theory, in this case closed strings, moving in this geometry in type 2B. Moreover, the order 1 over n corrections, so a 't Hooft has an expansion order 1 over n which organizes in terms of a genus of Riemann surface. The order 1 over n corrections are nothing but perturbative series of this string theory. So string perturbation gives you 1 over n corrections to gauge theory. Okay, so this was where things landed there. People then go back and ask, okay, what is the answer to the question we wanted to ask? Understand. What is the non-perturbative completion of string theory? Well, the answer people seem to give these days is that, for example, in this context, if you ask what it is in this context, the answer they say, oh, it's just n equals to 4 S3 Yang mills. I would like to basically argue that's, even though it's a correct statement, it's not the satisfactory answer. Because you see, it was the opposite. This was the easy side. This solved this problem. And in fact, perturbation expansion of this, which is hard to do from this side, is already doable in principle in string theory. That's where we started. Now to say the non-perturbative part of this can be answered by that is completely turning it around. So right now we are in the status where we don't have a good definition of what is ADS side. So if you call this the B and this the A side, we know what the A side is, but we don't understand the B side. So all we do is, you know what, A and B are equivalent, therefore any question in B can be answered today, but don't ask me what B is. That's where we are today, unfortunately. So this I don't find satisfactory. We are not in a situation where I would call we are in a good place. Namely, it is true that we can say B has properties like A, so we can say some general things about B. For example, it's not completely uninteresting. For example, A, if you're interested only in B, A can tell you, for example, unitarity makes sense, because here you can actually argue rigorously about unitarity of the theory, whereas it was not clear what B has. So there's some general feature you can make about B, but if you really want to understand B in its own right, A is not going to be very helpful. Some general features, yes, but not otherwise. I'll give you an example. It is somewhat similar to the T-duality I mentioned there. You see, to define a position on that dual space, you can do it, right? There is some way you can do it. Like you can take winding and take superposition of the winding modes to get the position. In the ADS-CFT, there's a similar problem. In that case, if you, for example, want to define ADS5, let's say, so there is this ADS5 geometry, the boundary is where the gauge degrees of freedom live. But the space has one more radial direction, so you want to have to describe what does each point in the inside means. Well, in principle, it should be possible from the boundary to define it, not in a very simple way. So the locality of the inside is mysterious from the viewpoint of gauge theory. Of course, it doesn't say it's inconsistent. It's just hard to describe it that way. That's not the right way to go about describing it. But that's the only way we can understand from this, is to try to describe what's called the bulk boundary correspondence, to try to find how you get geometry locality, and all the properties from inside by questions from outside, a little ad hoc. So people have spent a lot of efforts, and they have made great progress, by the way. Don't misunderstand me. They have done amazing work to try to write the analog of what I wrote down here about the relation between position and the winding modes in the T-dual one. But clearly, that's not the right way to think. If I tell you I want to send a wave packet around, it's very funny to think of it in the dual language. So I would say this is true, the duality is true, but not particularly helpful if you are interested in local question in the bulk, which is what we're after all interested. We are interested in local questions in the bulk. Questions having to do with the black hole evaporations and what's going on inside the black hole. These are questions deep inside the bulk. Questions similar to what's called firewall paradox and all the stuff that comes about in the context of these kind of models is exactly the problems that is very hard to understand what it is from the boundary viewpoint that we are doing. Okay? So this tells us that we are in an unfortunate situation. We have a definition of equivalence. We have, in principle, a definition of the B side, but we should have a direct definition of B side, and we have no idea how to define it. A duality is two different theories, well defined on their own right, and the equivalence is the statement of duality. Here we just have one theory, A. B doesn't exist. B is just doesn't exist, apparently. Well, that's not satisfactory. So we should find a definition for B. Okay, so what does this mean? What am I aiming at? Well, so now let me step back a little bit. Even before, perhaps around the same time, people were talking about, well, maybe even before string theory. So by the way, by now it must be clear what I mean by the missing corner to try to define what B is in its own right. That's the missing corner.
Can I make a remark?
Yes?
So I agree with everything you say 100%. I guess I just add to it that it's a little better than it could have been, that although we don't know D in principle, in certain limits we think we do know D, namely in the gravity limit. And in that limit, then we can match it to A and make non-trivial statements.
Sorry, what do you mean by the gravity limit?
The limit in which ADSI produces a common-theory to a class.
What is the definition of it? I mean, we're talking about three-level strings.
Right.
No, so my question is, define, so that's, if we had to say that, then we don't have any problem. We know that, I started by saying that perturbative string is not satisfactory.
Yeah,
So,
and I'm not disagreeing with you.
right, so now I'm saying that three level is good. It gives you Einstein's theory, so that's good. That's a solution to a strong coupling problem in gauge theory. That's the way I view ADS CFD. It's powerful, not for so much for ADS. It's powerful because of CFD. You want to have a hard problem in CFD to solve, and the ADS gives you a solution. You have a question about entanglement in CFD, ADS is a solution. Those are beautiful statements. But if you ask questions inside the ADS, like black hole and this and that, sorry about that. Okay? They're dual, but I can't help you with it, because we don't have a good description of B. So the B description is missing, and this point I think is missed somehow. In all our amazing happiness with ADS CFD, the fact that this is a big missing issue is not as much addressed. People try to say, all we can do is to start from the boundary because that's all we know. So people take a more practical viewpoint. Our understanding is engaged theory is much more robust. We understand it. Gravity is a big headache. We forget about it. We just do the boundary and hope that's enough to understand the gravity, and I think that's unsatisfactory in my view. Now, some people take the view that gravity is only an effective theory. It's just an effective theory. That sounds a bit strange, you see? Because as I started by saying, you could have said the same thing about string theory. You could have said, well, you have this perturbative series of strings. It's an effective theory. But the perturbation and all that make perfect sense. It is not just the classical terms. If it was just a classical one, if we didn't have a perturbation series which made perfect sense, you could have said it's just an effective theory. But it's very strange when you have a concrete scheme of computing to all orders in perturbation theory to call that just an effective theory. Now, in fact, I want to give more, since this issue is actually quite crucial, I want to give one more example about what this effective theory perspective means. So Seiberg and Witten solved the n equal to 2 vacuum geometry for S n equal to supersymmetric Yang-Mills for SU2 gauge group, let's say, in 4 dimensions. And they found very surprisingly that the solution was given in terms of an effective U1 theory, whose gauge coupling was a function of the parameter space of the it was related to the scalar vev of the adjoint field in the SU2 gauge multiplet. So they write this as an effective theory. So what they mean is that the infrared dynamics of this theory is described by not a well-defined theory, because U1 is not a well-defined theory, an effective theory with the tau. So this was not quite a duality either. This was just an infrared dynamics of one side being equal to the other. Somewhat similar to the viewpoint that people would say that U1 is just an effective description, not the full theory. It's not a complete theory. However, when you embed this problem inside string theory, both sides of them become honest string theories, complete string theories, not effective theories. For example, this theory, the first side is realized as a geometry involving P1 times P1, the one I was talking about yesterday, P1 times P1 inside the Calabi-Yau threefold. This is an SU2 gauge theory. And so this is the type 2A, let's say, on this P1 times P1 geometry. And it becomes dual to a type 2B with some Calabi-Yau threefold. So they are both on the same footing. And in fact, mirror symmetry, T-duality I was just telling you about, whose extension is mirror symmetry, gives you this duality. So they are literally on the same footing. They are literally on the same. You cannot say this side is fundamental, but this is just ineffective. So we learned in string theory that this realization of Seibert-Witten, where the U1 was just an effective description, in string theory gives you two honest, democratically equal theories, two sides. One is SU2 gauge theory, one is an effective U1 looking theory, but has its own completion in string theory. And they are related by T-duality. So this perspective is showing us that we do have really two sides in the Seibert-Witten side, and they are dual to each other in the same sense. We can describe them in the context of string theory as mirror symmetry or T-duality. Okay, so now I want to step a little bit back. So what are we aiming for? Well, what could gravity be? We are back to square one, right? I mean, what do we know about gravity? We are exactly the same place people were in, I don't know, 40s, 50s, when they started saying, what is quantum gravity? So they began to think like, well, what is gravity? Gravity is a fluctuation of the metric. But if you do a back of the envelope calculation, you find that the fluctuation of the metric at the Planck scale should be very violent. So not only the metric fluctuates just a little bit, it becomes big, and in fact the topology could change. So you have a fluctuating metric and topology at the Planck scale. Where is that? Where is that in string theory? How do we see that? How do we probe that? What is the Planck scale physics? We have no idea. We have no good description of Planck scale physics. But there was this idea that somehow you have to sum over topologies and geometries with some e to the minus the action, some action. And this should be somehow morally a definition of a quantum gravity. That's at least the most naive description. What could it be? Okay, what can such a thing be? We don't have such a description. Instead, we have dualities like mirror symmetry. We have large n stories, large n dualities, which give you such things that I explained. But we don't have this. This description is missing. We don't have such a description. Now, this is very amusing because you have to have a wide fluctuation of geometry and topology and metric and all that. But at long distances, somehow it should wash out. Somehow to look like a smooth, like fat space, or smooth like ADS, or some geometry which is smooth. That's already remarkable. How out of this bumpy kind of fluctuating, what you could call quantum gravitational foam of these geometries, somehow you're getting something nice and smooth, which looks like classical geometry emerges. So you have to have some mechanism where these fluctuations, while at Planck scale, becomes not so wild at the infrared scale, large distance scale. So people had thoughts about this. People have had thinking about this. There are attempts in trying to make sense out of these kind of pictures, but we don't have a satisfactory description of this. Okay, is that clear? So I hope I have phrased the idea of the missing corner as something which is not satisfactory about where we are today. So my basic aim is pushing the ADS-CFD to its limit will not answer the questions that we want. That's my main point. It is, and that's what people are attempting mostly these days, to try to push ADS-CFD to its logical extreme, to try to say everything from the inside from CFD, and it's getting more and more laborious to try to get the simple things from inside. Even the locality of the inside or causality comes hard to try to get it. Where there must be some simpler description, clearly. That's what we are trying to aim for. Yes?
Isn't it also the case that that is confined to a particular background, whereas what you would want is another?
Absolutely. That's another nice issue. So here you want to have something which you don't start with a background metric, and you want to. That also should be a description of some choice of a background. So in other words, you have a formulation which does not depend on background. Yes. But even if I start with even if you fix your background, even for a given background, I would still say I'll be happy if somebody told me within that background, like ADS, fix that background, give me a description of the full theory as a sum over geometries and topologies, such that perturbation of strings emerges in the usual way, in some way which completes that. How would you describe it? But yes, ultimately one would like to have answer to that, the one you just raised, which means I want to have all the solutions. That's in particular ADS and other Calabi and all that would be just examples of solutions, but there's a general framework. Yes? Somebody was asking a question. Yes?
So suppose that we have last space, and we're able to perturbably calculate.
Yes?
So what's the argument as to why that theory should be holographic as opposed to having so ADS-CFT is referring to sort of manifestly holographic, whereas
Yes. So what you're pointing out is a very good point. You're saying one of the amazing features of gravity, quantum gravity, we know is holographic feature. Things go like the entropy goes like area, one lower dimension. And this is somehow encoded in ADS-CFT. That's one of the nice features. Even though that does not quite explain, it doesn't quite explain why the black hole entropy is actually the area. It just kind of goes in that direction because of the holographic nature. It's of course an interesting thing how it would emerge from such a description. And I don't know, but you're absolutely right that would have to be some of the features that we have to explain. But to say that this doesn't exist just because of holography, I think is stretching it. In other words, that feature should be explainable in some reasonable way. Why is it that such sums over metric will have holographic features? That's undoubtedly one of the amazing discoveries we have made, that holography is an important factor about gravity. Yes?
So if the string scale is lower than the plane scale, is that all?
In fact, it's good that you're anticipating. That's exactly where I'm aiming at. So I will come to that question in a second. Okay, good. Okay. So people don't study this, as I mentioned, partly because we don't have good ideas, really, and partly because we do what we can, so to speak. So, and unfortunately, we don't know what to do with that. So, and I sympathize with that viewpoint as well. But what I want to point out is that there is one context where we actually know what to do, and we can make sense out of this. And indeed, it's a feature we have all of these things, but including this one, we can actually fill the gap. It's not in the context of the full string theory, but it's in the context of what's called the topological string theory. So in one context, this topological string theory, we know that there is an extra corner, and they are all equivalent descriptions of the theory. Okay? That's what I want to discuss, basically. So I have to tell you what is topological string theory. Well, topological string theory is a baby version of string theory you can think of. So you have, so let me just focus on one class of thing. You take a Calabi-Yau threefold, and you look at maps from a Riemann surface to Calabi-Yau. But this map, so if you take coordinates of Calabi-Yau, will be functions of positions on the Riemann surface, z and z bar. But you say, you know what? I don't want to have all maps. I only look at maps which are holomorphic. In other words, the Calabi-Yau has a complex structure. The Riemann surface has a complex structure. You just say the map should be holomorphic, map from holomorphic to another holomorphic space. So anti-holomorphic part of holomorphic maps vanish. In other words, xi is a function of z, and xi bar is only a function of z bar. So this is a baby version of string theory. You're restricting the class of maps. So these kind of string theories have been introduced by Witten a long time ago, and people have studied various aspects of this. For example, if you take a complicated Calabi-Yau, for example, what is called the quintic threefold, which is degree 5 hypersurface in CP4, you can actually not only compute these, you can actually sum up all, you can integrate over the shape of the moduli space of Riemann surfaces, what we really dream to do, up to genus, like, I don't know, 50 or 51, whatever it is, up to high enough genus. We are really powerful techniques to actually try to compute these amplitudes. So there we have made a lot of progress in understanding these, and they have proven to be useful for the full string theory. It turns out the amplitudes that you compute will depend on the following. You take e to the minus the area of the curve. So if you take this k as a Kähler class on the Calabi-Yau, and you integrate it over this, or if you wish, you pull back the, if you call this f, and if you pull back the Kähler class and integrate over the Riemann surface, this gives you an area of the Riemann surface inside. You sum over all such holomorphic maps, all such f's, and this is the partition function of topological string, which depends on the Kähler class of the Calabi-Yau, and also on G string. Namely, the G string part has to do with the fact that for every genus, you multiply this by the corresponding factor G string to the 2G minus 2. So for each genus, you weight with that, so you get a function of this. So this object, so if you take a connected piece, this you'd have to take the exponential piece of this. So let me just write it more precisely. It's like this. You take a fixed genus, you look at these guys, you multiply it by G string to the 2G minus 2, sum over all of these guys, you sum over f and genus, and then you exponentiate it, and that is the partition function of this topological string. Exactly. So you exponentiate it to take into account disconnected worksheets. Disconnected maps. Right, exactly. Okay. And these objects show up as computations of supersymmetry protected quantities in the full string theory. So for example, if you take the full string theory, let's say type 2a on Calabi-Yau threefold times R4, you get n equal to 2, 3, and 4 dimensions, and these computations correspond to doing some computations left over in R4 involving some supersymmetry protected quantities in the resulting n equal to 2 theory in 4 dimensions. So they are useful for the full string theory, even though they are on their own right a baby version of string theory. So here I don't want to talk about the usefulness of them in the full string theory. That you can read about if you're interested. But my main motivation here is that the baby's toy model for the full string theory that we want to understand in terms of the sum over topologies and geometries. That's the motivation I'm going to take. Yes? People have tried. There should be, I would say. And people have, in particular, in the context of M2 branes. I have also written papers on it. So people believe that there is a version of it, and we have proposed some versions. People haven't studied it as much, so we know much less. Yes? So that's called topological M theory. Yes?
Actually converged.
Sorry?
These sums actually converge.
Yes. Yes, actually, I will give you examples of how it converges. For the full case, we don't know, but the examples we know, so we believe the answer should be convergent. Well, it could be that since it converges, it can view there's no non-perturbative effects. That's correct. But there are versions. So as I said, I don't want to say that's definitely the case because it depends on exactly which way you complete it. So people have had different proposals of what does it mean to complete this. So let me, at this moment, just view this as a perturbative series. And I will actually focus on one very specific, simple case for this talk. So we can actually do gory detail of what it is. Okay, good. There's also dualities. Namely, it turns out this is sometimes called topological string theory, or sometimes it's called topological A model. There's also a topological B model. Topological B model is related to doing, instead of areas, the thing that's playing the role of the areas, Kähler class, which is the size of the cycles inside the Calabi-Yau, is played by the complex structure of Calabi-Yau. So in fact, it's the mirror of the same Calabi-Yau. So if you take the Calabi-Yau and do T-duality, then you get a theory which depends on complex structure instead of Kähler structure, and that's called the B model. So mirror symmetry or T-duality exchanges them. I won't describe the topological B model other than saying it just exists. So T-duality exists. So you have two dual theories and they're equivalent. And it's useful, in fact, in solving this model. So sometimes if you want to do this, this is very hard. And doing the B model is sometimes easier, and that's what sometimes people do. So this relates to the complex structure of Calabi-Yau. It's like doing complex structure of Calabi-Yau becomes dynamical, and you're describing things in terms of complex structures, and this is related to mirror symmetry. But I won't talk too much about it. I just want to say it's very much like the full string theory. You have one side, you have a dual side, no problem. Now, just like the usual string theory, these theories, the topological strings, topological A model, admits D-branes. They have D-branes. So in particular, there are Euclidean D3 branes. So if you think about this whole thing in Euclidean space, there are three-dimensional objects inside the Calabi-Yau. So if you take Calabi-Yau, you take some three-dimensional subspace inside the Calabi-Yau. So this is three real dimensions, Lagrangian, inside the Calabi-Yau threefold, which is complex three-dimension. You can put D-brane wrapped around it. So in fact, if you take D-brane wrapped around the three manifold, inside the Calabi-Yau, so Calabi-Yau is like locally near the M3, looks like cotangent of M3. So this is three complex dimension. And near this locus, so the M3 is the Lagrangian subspace inside the full Calabi-Yau. So the neighborhood of it looks like cotangent of M3, like a phase space. And you can put D-branes around it. Now I can use colored chalks, I guess. So you put n D-branes around it. And you can do topological string in this context. So all that happens is that you still do holomorphic maps, but the holomorphic maps might end on, there will be boundaries which end on these D-branes, just like the usual thing we do in string theory. Then you get a new sector, the sector of open string. The sector of strings stretched between D-branes, it gives you a new sector in your theory, just like the usual string theory. And you can ask, what is that? Well, it turns out that that theory living on M3 to first order is nothing but Chern-Simons theory of UN on M3, whose level is related to string coupling constant, or inverse string coupling constant. the same string coupling constant that defines topological string. Okay, so this is quite beautiful. So there's a Chern-Simons theory and so on. So it's a very rich subject. So you have a open sector, the gauge theory, and then there's gravity, just like the usual statement. So we should view these closed string ones as gravity. But what is the relation between this D-brane and gravity? How does it source it? Well, it turns out that it sources it the following way. If you take a D-brane, it is three-dimensional, and it is surrounded by a two-sphere, right? If you have three dimensions, the normal direction is R3. So if you think about this as R3, the normal to it is an R3 inside the Calabi-Yau. And so there's a sphere inside that R3 which surrounds this point, a two-sphere. And then you can integrate the Kähler class on this two-sphere, and it turns out to be n times G string. In other words, if you put n D-branes here, it sources the area of the Calabi-Yau by n times, by the number of branes times G string. So that's, you can think about this as a back reaction of the branes onto geometry, namely the Kähler class. Okay? So this is the analog of the flux formula. So the analog of the flux formula in this context is that the gravity degrees of freedom, the Kähler degree of freedom, is sourced, if you wish, by the D-brane. Yes? So this is a good question. So at this level, we are describing this as a power series. So in that case, it doesn't matter. But there are two answers to your questions. One is that whether this is Chern-Simons or complex Chern-Simons. In the complex Chern-Simons, K can be complex. So this is more the complex Chern-Simons, chiral version of Chern-Simons. Good question. But some people actually have used that view to say, oh, no, K has to be quantized, and there will be, to get a non-perturbative definition and so on. I don't think that's the correct one. It's a more correct version, I think, is just the complex Chern-Simons. Okay. Good. Now, so you might ask, wait, in the usual string theory, we have large N dualities, holography. What about this? Do we have large N dualities on holography? The answer turns out to be yes. So what do? Well, you take, I'll just give you the simplest example. You take a three-sphere, and so you consider the Calabi-Yau, which is cotangent of S3. It's a non-compact Calabi-Yau threefold. This is sometimes called the conifold. Take cotangent of three-sphere, and you wrap D-branes around S3. And it turns out that this theory is dual to O minus 1 plus O minus 1 bundle over a two-sphere, which I call P1, where the size of this, the Kähler class on the P1, is just n times G string. The fact that the P1 has a size given by n times G string basically is this statement. That is because what happens is the following. The normal geometry to S3 is R3. It's cotangent direction, right? There's an R3 here. And there's a S2 in that. So in other words, the boundary of this space is S2 times S3 at infinity. When you put branes over here, it's equivalent to changing the size of S2. This S2 is the same as this S2 I'm talking about here. And it's just like a holography, the S3 gets filled in. So this gets filled in to what? To this. This is the filled S3. Namely, filled S3 is a four-dimensional like R4. And this is two line bundles, direct sum of two line bundles, which means C plus C, which is R4. So this is exactly like the usual holography. That is, you have a theory whose boundary data is somehow sourced by a gauge field, but the theory involves, on the right-hand side, no D-branes, so just closed strings. And the data about N and all that is captured in terms of the size of this P1. How do we know this theory is true, this duality? Well, this is one of the cases we can actually check it to all orders in the 1 over n expansion. Both sides can be computed independently, and they match to all orders in 1 over n. Okay? Great. So we now actually understand holography there. So we have an example of holography, and we can use it to actually do much more. In fact, this holography in this language has been used to solve. So what I just described here is in terms of a transition between what people draw as an S3. So you can think about this as an S3 suspended between the branes, if you want to think of it that way, to a conical where the P1 is evolved. So this you can kind of think of two lines coming together, intersecting and opening up a P1, and this P1 is the one I'm talking about here. So this duality is kind of a local picture, and people have used this to generate computation of arbitrary toric geometries inside the Calabi-Yau by gluing these together. So you can actually answer the topological string for all what's called toric Calabi-Yau geometries using this Largent duality. So this Largent duality has actually been very helpful in trying to reformulate all the computation in terms of Chern-Simons, and so we can understand things very clearly. Okay? Any questions? Yes? O minus 1. So what this means is that the total space is Z and two spinors, lambda 1, lambda 2 on Z. So you can think about two spinors on the sphere. A spinor is basically what we call an O minus 1 bundle. So you take two spinors plus Z, that's three components, three-dimensional space. Yes?
So on one side, we have topological strings, and on the other
Yes. And they are dual. So just like the usual duality, one side is just pure gauge theory, and the other one is closed string gravity, topological gravity.
and in some sense, is there a relation? One of the down because the space
Yes.
and it
Yes. And also the observables, like the Wilson loop observables, and also it's much more. So people have studied the Wilson loop observable of Chern-Simon and mapped it to closed string computation, and that gave rise to what's called the topological vertex formalism for computing closed string amplitudes using that map. So it's very useful, not just the partition function, but also observables. So this is a very well-developed toy model, if you wish, for Largent dualities, because we can actually compute to everything, basically, in it. Okay, I think I have to speed up a little bit if I want to get to the main point I wanted to say. So all I'm trying to drive the point is that this is not just a boring toy model. It has actually all the features we're familiar in the context of a realistic string theory. Okay. Now I come to the main point. I'm going to talk about a very, very interesting Calabi-Yau threefold, namely C3. Okay? C3, it turns out this is interesting enough for our purpose. We can do more, you saw that. But it turns out for what I want to tell you, this does well enough. Let's just take the space to be boring C3. Well, you say, what is topological string? Well, topological string is holomorphic maps to C3. But there is no cycle to wrap around, so everything squeezes to a point. You just take constant maps. But still, you have to compute the space integration over the margin of Riemann surface, and you get some numbers out. So already, even this boring case, where every Riemann surface maps to just a point inside C3, turns out to be giving a non-trivial answer. And so it turns out that the partition function is given by computation of some Chern class of some bundle. I don't want to say the details. On the marginalized space of Riemann surface Q, on the marginalized space of genus G, you compute this number. You multiply it by string coupling constants I call G string, the 2G minus 2. You sum over all G, you exponentiate. So you get some function of G string. Okay, that you can in principle do. This is just some characteristic Chern class computation, G minus first Chern class computation of some bundle on marginalized space of Riemann surfaces, which I don't want to get into. But my main point is that there's some mathematically well-defined computation you can do for topological string, even constant maps. You compute it, you get the answer for the partition function, which in this case, since there's no sizes here, only is a function of G string. It's a very boring looking function. This can be computed. There's an explicit formula for these. Actually, it wasn't originally known, but we conjectured it, and it actually works. And mathematicians have proven it. And I will write down the answer for you in a suggestive form, even though I can write down what these are. These are related to Riemann zeta function objects. And you sum it up and you write it in a more suggestive form in this way. Where Q is e to the minus G string. That's the answer for topological string in this case. Okay, so we can do the answer in terms of the usual string perturbation theory. Now I ask you, what is the other description involving quantum geometries and sums? Is there an analogous description involving that? Okay, that's the answer we want. That's the thing we want to answer. So I want to actually re-understand that in a completely different language. That final answer, I want to think about it very differently. So then I will just come up with what do I mean. So now I have to give you what is the sum over geometries, what do I mean by geometries and all that. I have to come up with that picture. So first of all, the classical action, what is the analog of e to the minus s? What is this e to the minus s that I had in this context? The classical action that we have, the s part, turns out to be nothing but the volume of Calabi-Yau divided by 1 over G string squared. Reasonable enough, right? Instead of the curvature, it gets like a cosmological constant term, if you wish. So it's a volume over G string squared, which is the integral of the cube of the Kähler form divided by G string squared. That's it. So this is kind of like you have to regularize it. You have to add the constants. If it's non-compact, you have to say the variation of it. That's correct. Okay, fine. So that's roughly the action. Now, what do I mean by geometries? Well, we saw from this description of D-branes, the D-branes in the topological string source the Kähler form, the size of the Calabi-Yau, but in quantized units of G string. So it suggests that somehow the sum over geometries involves quantized areas. You have chunks. Okay, so we'll make that conjecture, that we postulate that these geometries are actually do not have continuous values of area. They only have areas multiples of G string. So the K should be written as n times something which is integral things. I would call it f. So the f has only integral values can only take integral fluxes basically, but I can write k as n times that. So let me write k as n times that. G string times that I meant, sorry. So f is integer, so f could be any n, but that analog of the G string is n G string is just f times G string, where this is the integral of some flux, integer valued flux. So I rewrite this in this form, and this becomes just G string times f wedge f wedge f. Okay? So this is basically C1 cubed, the first Chern class cube, of that f, if you think about f as the curvature of a U1 gauge field. So I would just say, look, I'm going to think about K as the curvature of a U1 gauge field. This is like gravity degree of freedom. I'm not rethinking in terms of a bizarre language, if you wish, in terms of a U1 gauge field, which gives you the role of quantization of area. Okay, good. So basically then I can rewrite the action as e to the minus G string times C1 cubed. The number of the integral of C1 cubed over the geometry, over the cycles that we have, is another way of writing of C. Or in other words, it is q to the power of, sorry, sign, I'm not being careful here, but q to the power of minus C1 cubed. Whereas q is defined as e to the minus G string. That's another way of saying it. Okay, so now we want to see what does this have to do with our rewriting of the answer. for that, we have to visualize C3 in a very interesting way. C3 is C times C times C. And I would like to rethink about what C is. Well, C is made of a radius and an angle, right? You can go to the two-dimensional plane, write it as a radius and theta. And I want to rethink this in terms of half a line with r bigger than or equal to 0, and thinking about this, the theta part, as a circle which shrinks as you go towards r equals 0. So I will just draw C in terms of a half a line, remembering that there's a circle which at the boundary of it shrinks to nothing. Okay, so what is C times C times C? Well, each one is a half a line up to this corresponding circle. So C times C times C can also be viewed as a corner of a room, and the room itself, well, basically you just take three half lines and you take a product of them. Okay, so this is C3. Okay? Where there's a three-dimensional torus, everywhere else, at every point except on the lines or faces or the points, there's a T3. On each face, the T3 becomes a T2 because one circle shrinks. And on each line, two circles shrink, so you just have an S1. And at the point here, all the three circles have shrunk to a point. So this is what's called the toric geometry representation of C3. You just encode it in terms of this diagram. Okay. Now, this problem, C3, has a circle symmetries, which is the T3 geometry. So you can actually use the symmetries of the problem to use the translational symmetry of C3 to actually say, as long as you have a circle symmetry left over, the partition function vanishes. So everything actually is coming from a point here, the contributions of a point here, where all the circles have shrunk. Because if one of them is not shrunk, you can actually show the answers are trivial. You get a trivial answer. So everything is coming from the corner, the very corner of the room. So what we want to do is to sum over quantum geometries of bubbling up of this point in terms of non-trivial quantum geometries. So, for example, you can replace this point, you can replace it by P2. You can cut the corner. Okay? This corner can have, this P2 can have various sizes, but from this condition, we know that the sizes are limited to be, we are taking a postulate that's integer units of G string. So you have chunks like this, like this, like this. You can have different units of size. Okay, so we can chop one point and then take these sums like this. Or you can take a more interesting geometry where you chop more than one piece. For example, you can chop a P2 and another geometry and glue them together like this. In other words, I'm describing for you the quantum gravitational form that I was telling you about. We can actually describe these geometries in terms of bubbling up of objects which would be putting there. So what do I want to do? I want to sum over all these bubbling ups of all possible geometries you can put there, weight with q to the c1 cubed, which is q to the area. Okay? Well, there's an overall volume, so the leftover volume is basically the leftover areas related to the pieces that I have chopped off. So it's q to the minus the number of chopping off you can do. So that would be the corresponding program one wants to carry out. Okay. So what is the answer? Well, it turns out that if you just did actual geometries, and you sum over all possible geometries, which could be very, very complicated, then you don't get the correct answer. So if you take naively what I just told you, just take the quantum gravitational forms of this theory with this postulate and just do the sum, you won't get the answer that we were asking here. However, you can generalize what you mean by quantum gravitational foam to mean a relation of it to a particular f. Namely, you can turn on, said differently, you can actually say what are the conditions for having a particular f on a given geometry. You can replace this by saying I'm actually doing a U1 gauge theory on C3. Sounds very boring. U1 gauge theory on C3 with some Chern classes. So this is actually not the usual U1 because you have zero size objects. So they have these sheaf-like objects, which are not allowed in the usual U1 gauge systems, but here it's allowed, which to make sense out of them, you can blow up the geometry to make them honest line bundle. So there's a relation between gauge theories like this, geometries like this, and field strengths, which could have these sheaf-like singularities, by basically blowing up to make sense like this. So you can say for each f, you can get a geometry, but not for all of the f's, for the opposite. For every such geometry, you can get an f. That you can do. But there are more f's than the geometry, so you have to extend what you mean by allowed geometries. Not in a dramatic way, but you still have to extend it. And in fact, from the viewpoint of f, it's actually a very simple answer. It turns out these are counting the holomorphic sections of a U1 line bundle on C3. And holomorphic sections of a U1 line bundle are easy to understand. Why are that? What is the description of that? This is very easy. And the description is the following. If you take a trivial line bundle on 3 dimensions, a holomorphic section of the line bundle is very easy. It's any polynomial in Z1, Z2, Z3. So they are generated by all possible positive integers. In other words, you can think about holomorphic sections as nothing but a lattice, if you want to think about like atoms, which are just put in atoms as a crystal, as a corner of a crystal in a corner of a room, and these are in one-to-one correspondence with holomorphic sections of U1. If you change your f, it corresponds to changing what are the holomorphic sections, allowed holomorphic sections. For example, if you say that no longer the n1, n2, and n3 equal to 0 is no longer allowed, it corresponds to deleting this point. And this is indeed related to the P2 blow-up geometry I told you about, with the size Kähler class equals to G string. So if you have a Kähler class of the P2 being G string, it is the same thing as saying I have deleted the point corresponding to n1, n2, and n3 equal to 0. That's not allowed anymore. In other words, if you want to write functions on this space, you just write arbitrary functions, except you delete the constant one. So that's the way physicists should think about it. That is, complicated geometry, all you just say, oh, you know what? It just means the function field space is changed. The field is no longer arbitrary functions of z, but they delete some possibilities. That's certainly easy to understand, and it's easy to handle. You could say I sum over all possible ways I can define a function on this space. And that turns out to be the correct generalization of what we mean by quantum geometries. It can be reinterpreted in some cases as geometries, but actually generalizes it. So we say the geometry is changed so that what we mean by a good function is changed. That's what the algebraic way of saying it is. So you basically start eliminating points from the corner of a room. So one point you delete is just this one. So that's one way you can do it. And then you can delete, so first of all you delete nothing, sorry. And then you delete 1. And then you can delete 2. You can delete these 2 or these 2 or these 2, basically by saying what are the powers which are excluding from allowed functions. And then there are 3 ways to do that, and so on. Okay? This turns out to be exactly identical to this, which is related to that funny sum. Yes, it's combinatorics. It's called what's called plane partition. So you just basically do some partitions. Generalization of Young diagrams from 2D to 3D. This is basically a sum over 3D versions of Young diagrams. That's it. It says that if you sum over Young diagrams with q to the power of the number of number of elements, you get that function. And that's being now interpreted as a sum over geometries. But now you see what is the lesson we are learning here. So we see that we can reformulate a would-be quantum geometry in terms of a U1 gauge theory, well, more fancy version of U1 gauge theory, where sheaf-like object is allowed. Or if you wish, you can think about this blow-up geometry. There are some possible regions of this U1 which do not correspond to honest geometry. So you have extended what you mean by geometries in order to do quantum gravity in this context. So what is the lesson we can learn from this for the full string theory? Well, it says that maybe the way to think about it in terms of the thing is like this. So suppose you take type 2B strings. I've just started with an example. You take functions on the space. Good. Suppose instead of functions on the space, you say space is not like R10, but it's R10, except I can allow changing of functions, what kind of functions I can put, like deleting some power series in terms of coordinates somewhere, and some overall possibilities like that. That could be a version similar to what I'm saying here. So I don't have a precise description, of course, otherwise I would have told you, but this doesn't sound like it's impossible. The fact that we could do this in this topological string and get the full answer in a more elegant way tells you that this is perhaps a powerful way. By the way, this way of reformulating topological string is not called the Donaldson-Thomas formulation of it, which is in terms of a U1 gauge theory, and you can generalize it to arbitrary Calabi-Yau and all that. So it is the most powerful version. It's probably the way people think is the correct version now of thinking about this topological string language. This is the way. So there's a U1 gauge theory. So this actually illustrates the lesson we learned. We had large N. Large N was powerful. Large N duality holography gave us some insight, but ultimately a good description was not that. The good description ended up being something close to sum over geometries, which is what you would have thought should be the right one. But now, before I end, I will answer the question just in a second, but before I end, which is I have a minute maybe, I just want to say the question that was asked by you about how the geometry emerges. I didn't get a chance to tell you about that. So you see, this is like thermodynamic sum, because you're summing q to the power of the number of points that you're deleting of the geometry, and you're summing them. So you can think about this as like q to the minus e to the minus beta, and n is like energy. So it's like a Boltzmann sum. So then you can delete these points, and there's an average geometry, average shape of deletion. So it's like a crystal, you're starting melting it, depending on what is the value of beta or q. If q is very close to zero, temperature is 0, or beta is infinite, then you don't melt anything. You get the crystal. If you start to melt more, you get a different shape. So you get different scales depending on the values of G string. And the size of how much of the crystal you melt depends on that. So it turns out the following picture emerges. So this is the length scale. So for lengths much bigger than L string, you get a shape which is just the corner of the room itself. You don't see anything melting. At the string scale, you see a modified smooth geometry where the crystal has molten a little bit here. And this is the alpha prime, what we call the alpha prime corrections to C3. So C3, this corner of a room is not viewed by a string perspective as C3, but by kind of a new geometry, the stringy geometry. But that's not the Planck geometry. The L Planck, which is G string times L string, which is smaller than L string, is this funny little foam here, made up these kind of funny pictures depending on what you're melting. So it's very, very jaggedy. So depending on the length scale, you have this Planckian thing, you have the string one, and you have a classical geometry emerging from this simple toy model. So this is the model I have in mind for the full string theory. The classical one, the stringy version, and the actual quantum Planckian one, which ultimately can explain the other ones. So that's how it could emerge, is in this way. So I think I'll stop here. Thank you. Then it's honest geometry. Yes, there is. Good question. So I will just answer it in terms of the Young diagram. So when you have Young diagrams, you can think about, this is just the 2D version of it. You just delete points, basically, just on this one. So you get, if the objects that you delete is like this, then there's a geometry. If it's like this, the corner of the other curvature, there's no geometry. So it's just generalizing the meaning of geometry. So it's roughly half of them are geometries.
Should we think about this sum over holographic line bundles as sort of summing over fluxes you can put on?
Yes, exactly. That's the way to think about it. You can trade the choice of the flux with the choice of the geometry. That's a one-to-one correspondence. For the cases where the flux is actually geometrizable, which is not always. Well, I don't think there's really a conceptual one. It's the question is, what is the analog of F? Sounds like you have an analog of some funny gauge theory that replaces the whole thing. Sounds like loop quantum gravity. No, I'm just forget about this. I don't know what's the answer. The main point is that we should be open. My suggestion is not to close ourselves into one particular path of understanding quantum gravity. I don't know what the answer is.
Do you have any mirror description of this?
I have not tried to do it, but I think it should be possible. I don't have a mirror description, but there should exist.
You mentioned the question of locality. There's something you can say in this context.
Well, that's going to be harder because these are topological. So the notion of propagating of a wave inside the Calabi, a topological Calabi, is harder. But yeah, so there's some things you can say. Let me just try to. Let me think. I did have some thoughts about it, but so as I said, this one is dual to this large N business of a S3 with Chern-Simons theory. So you have S3 N D-branes, which N on S3 gives you these guys. Now, you would want to say, I want to probe the inside of this geometry, which means that you want to probe a point on this P1. So that somehow the analog of the bulk geometry and locality in that case will be related to understanding how can you see the P1 from the perspective of this other gauge theory. And it turns out that one way you can try to do it is in terms of Wilson loop observables of this theory, but you have to get higher and higher ranks. You cannot stop with fundamental. You have to take a very large representations in order to try to probe inside. So that gives you a perspective that in order to localize points inside, you need to take more and more higher and higher observables with higher and higher ranks. This is somewhat like the winding mode business, where you have to sum over all the windings in order to localize a point. This is a suggestion that this picture would sell, that in the usual holography, perhaps higher representation should be an important aspect of trying to define the inside.
Are people trying to do it?
I'm sure they are. I'm sure they are trying, yes.
Yes.
Yes. Yes. Nothing. Isn't that surprising? Well, I shouldn't say nothing. What has been shown is that indeed the good description of topological thing is this U1 gauge theory. And mathematicians are just using that picture nowadays to try to compute things. So that's a problem. So we know that's the right formulation. But physicists, unfortunately, have not caught on the developments. And they are not, I think, in the physics literature, there hasn't been much description of much more progress. And in particular, application of these kind of ideas to the full string theory. There's no paper. There's no paper.
Maybe we can wrap it up after this beautiful set of lectures
Thank you.
and thank Cumrun for the data.